Second speaker of this morning session is Professor Michael Hutchings from UC Berkeley. Professor Hutchings is an expert in contact geometry, maybe in many other topics as well. Right. Okay, so let's welcome. Okay. Yeah.
All right. Well, thank you very much to the organizers for the invitation to this great conference at this exciting place. So this talk is supposed to be accessible, so feel free to interrupt with questions about anything, no matter how basic. So I want to talk about symplectomorphism invariants. Of open domains in R2n. So what do I mean by this? So in R2n, we have the standard symplectic form. So omega is from I equals 1 to n, dxi, dyi. And then suppose I have two open sets, u and v. So the symplectomorphism, so if u and v are open sets in R2n, the symplectomorphism v from u to v is a diffeomorphism which preserves the symplectic form. So phi star omega equals omega. So then I can say if I have two different open sets, is there such a symplectomorphism or not? So how can we decide the two open sets are symplectomorphic? So, well, one obvious necessary condition is that they have the same volume. And that's because the symplectic form determines the volume form. So if you wedge the symplectic form with itself n times, you get n factorial times the Euclidean volume form in R2n. But this condition is far from sufficient. Now, so this particular question hasn't really been studied that much, I don't think. So there's been a lot more work studying symplectic embeddings. So sort of modern symplectic geometry basically started with Gromos non-squeezing theorem. From 1985. So we define the ball to be the set of Z in R2n. So I'm thinking of R2n as Cn, such that, and then symplectic geometers have a slightly funny convention for what the radius of a ball is. So in symplectic geometry, this means that pi times the absolute value of Z squared is less than R. Or you could do a closed ball if you like. So it's the ball, so if you, the sort of the two-dimensional radius is R. And then the cylinder Z of R is z in Cn such that I times the absolute value of the first coordinate squared is less than or equal to r. So the ball looks like this. And the cylinder looks like this. So it has a two-dimensional slice of area r. So what Gromov's non-squeezing theorem says is that if there exists a symplectic embedding, B of little r into Z of big R, then r is less than or equal to, little r is less than or equal to big R. So the ball, now, so symplectic embedding is defined like a symplectomorphism, except it's just as smooth embedding, which respects a symplectic form. So for a symplectic embedding to exist, it's again a necessary condition that the volume of this is less than or equal to the volume of that. But this has infinite volume, so clearly the volume condition is satisfied. But if the ball is wider than the cylinder, then you can't squeeze it. So this sort of started modern symplectic geometry. Since then, there's been a lot of work studying when symplectic embeddings exist. And some of the tools developed for that can also be used for this question about symplectomorphisms. But I'll make a remark. This is kind of complicated. So if U and V are open sets of the same volume, it is possible that there exists a symplectic embedding from U into V, but no symplectomorphism. So an example is, well, I don't have the notation yet. I can show you an example later. But there are examples where, like U symplectically embeds into V, but it's sort of folded up in some complicated way. So the complement of the image is some measure zero set, but it could be complicated. So there isn't a well-defined inverse map from V to U. You'd have to remove some subset. Okay, so that's sort of a warm-up. So let me state a couple of theorems. And I can tell you what kind of tools we can use to approach these. So I have to define a family of examples that I'm going to look at. So let omega be a subset of Rn, not R2n, but Rn, where all the coordinates are greater than or equal to 0. And I define the toric domain x omega is z in Cn such that pi times absolute value of z1 squared through absolute value of zn squared is in omega. So for example, let's look at some n equals 2 examples. So if I take omega to be a isosceles right triangle of side length r, in this case x omega is the ball B of r. If you take a triangle with side lengths A and B more generally, then this is an ellipsoid, which we denote by EAB. So it's pi times absolute value C1 squared plus pi absolute value C2 squared over B is less than or equal to 1. Another example is you take a rectangle of sides length A and B. Then this is a polydisk or a bidisk. So it's a Cartesian product of two disks of areas A and B. I can tell you, now I have the notation, I can tell you what my example is here. So the example where you can embed U into V and they have the same volume, but you can't go the other way, is U is E of 1, 2, and V is the polydisk P of 1, 1. Okay, so this is a family of examples, and we say that X omega is a convex toric domain if when I take the set omega hat, which is defined to be X in Rn, such that absolute value of X1, comma, absolute value of Xn is an omega, then this set is convex. So these are all examples of convex toric domains. So in general, you can think of a convex toric domain as looking something like this. So you take the set omega, you take the union, sorry, this is bad. I shouldn't have drawn lines there. Okay. So you take the set omega, and you take its reflections across the axes. That whole thing is omega hat, and you want that to be convex. So that's just a nice family of examples that's been studied a lot. The terminology is a little bit problematic. So it's true that a convex toric domain is a convex set in R2n. However, there are toric domains which are convex sets in R2n, which are not convex toric domains. I apologize for that. Anyway. Yeah, you can take something, if it's, you start with the ball and then you just sort of replace the ball, place it with an LP ball for P slightly less than 2, then that's the toric domain is the convex set. Okay. So an example where omega is convex but omega hat is not convex would look like this. Okay, so I started thinking about this because somebody asked me, hey, could it be true that every reasonable domain is symplectomorphic to a toric domain? Because sort of there are various conjectures in symplectic geometry, and all conjectures are true for toric domains, so that'd be helpful. I said, well, I don't think that's true, and they said, well, prove it. So theorem 1 is that there exists a toric domain X omega in R4, sorry, not a toric domain, excuse me. The whole point is it's not a toric domain. There exists a star-shaped domain X in R4 with smooth boundary You can also choose it arbitrarily. C infinity close to a ball. Such that the interior of X is not symplectic, symplectomorphic to the interior of X omega, where X omega is a toric domain with smooth boundary. Star-shaped is actually redundant in the way I stated the theorem, but star-shaped means that if you have a domain with smooth boundary, then in symplectic geometry, star-shaped means that if you take any ray through the origin, then it intersects the boundary of the domain transversely. If it's C infinity close to a ball, then this is automatically true. Okay. And by C infinity close to the ball, I really mean that the boundary is C infinity close to the sphere. Okay. So you can take the ball, you can perturb it a little bit, and then it's not toric anymore. And the proof of this is in the preprint 24020733. And the proof is going to use a zeta function, which I'll tell you about in a minute.
One last question. So for the star-shaped domain, so the given points are supposed to be the original point, right?
Can you repeat the question?
So for the star-shaped domain, I guess the definition is every so given one point, then the other point connects to this point, the line section that belongs to.
Well, that's convex. So convex will imply, if it's convex with smooth boundary, that implies star-shaped.
Yeah, but star-shaped rectangle, the definition may be my understanding wrong.
So it doesn't have to, like this example I drew is star-shaped, but it's not convex because there are 2 points here where the line between them has to go outside of the domain.
Okay, the definition of the star-shape, I guess there's maybe the given point, right? So every other point.
So the origin. So every ray from the origin. The classical definition of star-shaped is just that. Yeah, but in symplectic geometry, I require a little more. I actually want the ray to be transverse to the boundary.
Domain X supposed to be omega here, or you're notation X of omega?
So here X is a domain which is not toric. I'm saying, so if X omega is toric, then this X omega is not symplectomorphic to X. Okay. So in general, X is any domain, and X omega is a toric domain. Okay, sorry about that. I appreciate the questions. If everybody's lost, then I'm just wasting my time, right? So, okay. Yeah.
X is not that symmetric, then is it obvious? If X is not symmetric for the original point, then is that statement obvious or not?
Is which statement obvious?
The theorem, if we just take X as a non-symmetric.
Well, no, not necessarily, because there are lots of symplectomorphisms. So, you could start with any domain, and you can take any, formally speaking, the tangent space to the space of symplectomorphisms is the space of Hamiltonian vector fields. So I can take any time-dependent Hamiltonian vector field, and I can move my domain around quite a lot. So even if it starts out symmetric, it won't be anymore. Okay. Good. All right, so theorem 2. So let X omega and X omega prime be generic convex toric domains in R4. In the generic, there's a precise condition that I want them to satisfy, which holds generically. I think maybe one can drop it, I'm not sure. It's an annoying technical thing. Anyway, if x omega and x omega prime are two convex toric domains, if they satisfy some technical condition which holds generically. So if the interior of x omega is symplectomorphic to the interior of x omega prime, then omega equals omega prime, or omega equals r of, it's a bad letter, let's say f of omega prime, where f of xy equals yx. So the symplectomorphism type of the toric domain determines the toric domain up to reflection of omega. Obviously, you can reflect omega to get another toric domain, which is symplectomorphic under switching Z1 and Z2. So the proof of this is in progress. I'm still writing that down. And this uses something a little fancier. So it uses barcodes on contact homology, which I'll tell you about if we have time. It's a remark. So in the special case, where the boundary of omega and the boundary of omega prime is real analytic, theorem 2, was proved by Moati in the 1990s. So this was actually, I only learned about this work a couple of years ago, so it anticipated a lot of later developments. So actually, if you read the proof, what he really showed is that the proof shows that the symplectomorphism type because you say, okay, where's the real analytic coming in? The proof shows that the symplectomorphism type of the interior of x omega determines the germ of the boundary curve where it intersects the line x equals y, and they're both greater than 0. So you for the convex toric domain, you take this line x equals y, you see where it hits the boundary, and this work of Moati shows that the symplectomorphism type of the interior of omega determines the germ of the curve right there. But this theorem says that, at least generically, the symplectomorphism type determines the entire boundary curve. Yeah? One could conjecture that the same is true in higher dimensions. So that was a good challenge problem for somebody else. Yeah?
Small question. So are these two theorems in the same dimension, or the first one is?
Yeah, they're both in R4.
X or the domains are?
The domains are both, yes, the domains have to be the same dimension.
So the polytope is dimension 2 and the symplectomorphism.
Yeah, so for the toric domain, like the omega it's a moment map image, so it's half the dimension. Why? So yeah, so my, well, yeah, this one I think I could do in higher dimensions. This one, well, the calculations get more complicated. It's reasonable to conjecture that it should work. So it's just sort of what I can compute. Yes? Okay. So what does generic mean? Can I return to that question later after I've introduced more notation? Well, theorem 1 says that they aren't, at least in 4 dimensions.
But that's not something. So the stochastic domain is not, you can get convex.
So yeah, the example it's convex. Yeah, I can tell you examples. Once you see what the zeta function looks like, it's easy to write down examples.
We already discussed that invariant is identical case, or we also use it in smooth case.
So my theorems are true in the smooth case. Right. So that's what Moati did in the 90s. So I'll just yeah. So that I think his argument proves that in the smooth case. I think that's what he proved. Okay. So let me tell you about the zeta function. So to prepare for that, so let X be a star-shaped domain with smooth boundary. And I'll denote the boundary by Y. Okay, so there's a contact form on Y, which is defined by lambda equals a half the sum from I equals 1 to n of xi dyi minus yi dxi restricted to y. So this thing is a standard Liouville form on R2n. It's the d of it is omega, and you can check that it satisfies the condition that lambda wedge d lambda to the n minus 1 is positive with respect to the orientation on y given by the boundary of the domain. And so this is sort of equivalent to it being star-shaped. And this determines the Reeb vector field. So it's characterized by d lambda of r comma anything is 0. So here, this is any tangent vector to y. So the fact that lambda wedge d lambda to the n minus 1 is non-zero tells you that there's this Reeb vector, there's a one-dimensional subspace of vectors R satisfying this condition. And then we normalize it by setting lambda var equals 1. This normalization is actually going to be quite important for what we're doing. Now, I'm concerned with periodic orbits of this vector field. I define a Reeb orbit as a periodic orbit of R formally to map gamma from R mod Tz to Y for some t bigger than 0, which is the period, or it's sometimes called the symplectic action. Such that it's a trajectory of the vector field. And I consider it equivalent if you translate the domain. So it's just it's a circle in Y, which is tangent to the vector field. You are allowed to go around this circle multiple times. So this map gamma doesn't have to be injective. So I define d of gamma to be the covering multiplicity of gamma over its image. So there's been a lot of study in contact geometry about when, like, do these periodic orbits exist? What can you say about them? So the fact that or the statement that they always exist is the Weinstein conjecture, which is true at least for star-shaped domains in R2n. So, well, for me, I'm not going to try to prove anything about Reeb orbits, but I'm going to use them to define invariants. Okay. Now, we say, well, if you have a Reeb orbit gamma, there's a linearized return map which I'll denote by P gamma, which goes from the tangent space to Y at gamma of 0 to itself. So this is the derivative of the time t Reeb flow. And actually, what I really want is to look at the kernel of lambda restricted to the space. Okay, so this is a 2n minus 2 dimensional vector space. It has a symplectic form determined by d lambda. So this is a 2n minus 2 by 2n minus 2 symplectic matrix after you choose a suitable trivialization. And we say that we say that gamma, is non-degenerate if 1 is not an eigenvalue of this matrix. And we say that lambda is non-degenerate if all Reeb orbits are non-degenerate. And that holds for generic contact forms, or in the case where the contact form is the induced form on the boundary of a star-shaped domain, it holds for generic star-shaped domains. So if I have any star-shaped domain, I can perturb it a little bit until all the Reeb orbits are non-degenerate. Okay, so now I can give you a definition of a zeta function. So definition, so if lambda is non-degenerate, define zeta of x to be the following thing. It's going to look a little weird. So I'm going to sum over all periodic orbits. So this notation means the set of Reeb orbit. And there's a sign, which I'm going to denote by -1 to the epsilon of gamma. So -1 to the epsilon of gamma is well, it's the sign of the determinant of 1 minus p gamma. So this is the kind of sign that arises in the Lefschetz fixed point theorem. So any Reeb orbit, if you take a little disk transverse to the orbit, there's a return map from the disk to itself, and the Reeb orbit is a fixed point of that map from the disk to itself. And this is the sign that would appear in the Lefschetz fixed point theorem. Then I multiply by t to the symplectic action of gamma. So this is some positive real number. And I divide by d of gamma. So this is a positive integer. That's the covering multiplicity. So this is some formal power series where the power series are, where the exponents are positive real numbers and the coefficients are rational numbers. And well, that's not good enough. So now we're going to exponentiate it. Okay. So where does this thing live? So this is an element of the universal nova covering with rational coefficients. So this is the ring of formal power series where the exponents are real numbers, the coefficients are rational, and you only have finitely many terms with exponent below any given upper bound. Okay. Okay, so that's a weird formula. So in fact, although it's not immediately apparent from this formula, zeta of x is an element of the nova covering with integer coefficients. And the reason why this is true is there's a product formula. Zeta of x is the product over gamma, a simple Reeb orbit. So these are simple Reeb orbits. So simple means that the covering multiplicity d equals 1 of 1 plus or minus t to the action to the plus or minus 1. And there are two signs here, and these signs are determined by the eigenvalues of the linear Rice return map. Okay. So that's the zeta function. It might look a little weird, but it's actually, well, where it comes from, it sort of goes back to a paper of Andre Weil in number theory. And this is sort of a descendant of that formula. So the theorem Why is well, so the kernel, so the tangent space is the sum of the Reeb vector field and the kernel of lambda. And the flow preserves lambda, the lead derivative of lambda is 0. So all that whole decomposition is preserved by the flow.
The kernel is a transfer space.
That's right.
And what's the action?
Well, it's what I said. So I mean, the p gamma is a derivative of the time t flow. The time t flow preserves the decomposition of the tangent space into the Reeb direction plus the kernel of lambda. So it restricts to a map from the kernel of lambda to itself. Sorry, I didn't say that very well. Yes? Why is it symplectic? Well, the symplectic form is given by d lambda, and again, the lead derivative of lambda with respect to the Reeb vector field is 0. Preserves that symplectic structure. D of gamma. This is the covering multiplicity of gamma. So it's a positive integer. If gamma goes around a circle once and it's an injective map, then D is equal to 1. If I go around the same circle 3 times, then D of gamma is 3. What is what? Exponent. Oh, this exponent here, yes. Action of gamma. Sorry, I should have said that. So that's the symplectic action, or a period. So the information that's going into this formula is what are all the Reeb orbits, what are their periods, what are their covering multiplicities, and what are their Lefschetz signs. Okay. So theorem. If X is a non-degenerate, star-shaped domain in R2n. So non-degenerate, I mean that the contact form of the boundary is non-degenerate. Then zeta of X is a symplectomorphism invariant of the interior of X. So if I have two star-shaped domains, non-degenerate, if their zeta functions are the same, sorry, if their interiors are symplectomorphic, then the zeta functions have to be the same. So the interior of the domain is seeing all this information about the Reeb orbits on the boundary. Now this isn't really very obvious because, like, let's say I have two star-shaped domains, X and X prime. Well, they look the same the way I drew them, but they're supposed to be different. And suppose I have a symplectomorphism from the interior of X to the interior of X prime. Well, like, I could take some, like, I can exhaust X by by scalings of X, which are slight shrinkings of it. But I could take some slight shrinking of X and see where the symplectomorphism maps it. But it could map to some very complicated thing in here. Okay, it's got to have the same volume, so I shouldn't. Anyway, you get the idea. So this could be quite complicated. This image certainly doesn't have to be like C1 close to the boundary in any sense. So on the face of it, the Reeb vector field in here could be very different from the Reeb vector field on there. Nonetheless, the symplectomorphism type still sees all this information in the zeta function.
When zeta X are invariant, then can we say that the two star-shaped domains are symplectomorphic?
The converse is definitely not true for an example I'm about to show you. So, right. So I have good news and bad news about using this zeta function to try to classify things. Before I can tell you that, I should say that, well, a couple of remarks. So Seeley-Bach for Hofer-Zander showed in the 90s that if X is non-degenerate, then the symplectomorphism type of the interior of X determines the multi-set of pairs action left at sign where gamma is a Reeb orbit. So their work sees most of the information in this formula. It sees the epsilon of gamma, it sees the E of gamma, but it doesn't see the D of gamma. And then I have a more general theorem. So the above theorem generalizes to dynamically tame star-shaped domains. So this includes degenerate cases when they're not too bad. In particular, it includes toric domains, because toric domains are degenerate, as we'll see in a second. So here's an example. So if X omega in R4 is a toric domain, so now I'll draw it like this. So it doesn't have to be convex or concave. I guess it has to be star-shaped. So it has some boundary curve which meets the x-axis at point A comma 0 and meets the y-axis at the point 0 comma b. In this case, then I can tell you the zeta function. So it's 1 over 1 minus t to the a times 1 minus t to the b. That's it. So it's sort of good news and bad news. The bad news is, if you want to try to use this to classify toric domains, that's not very good, because it tells you almost nothing about the toric domain. It only tells you where the boundary curve meets the axes. The good news is that it makes it very easy to prove that lots of examples are not symplectomorphic to toric domains, because in fact, almost anything you write down, the zeta function is going to look a lot more complicated than that. It's kind of a special thing for toric domains that almost everything cancels in the zeta function. Multiset. So I'm saying you look at all for every Reeb orbit, you write down this pair. You get a bunch of pairs, but some of them could be repeated. There could be several Reeb orbits that have the same action and epsilon. And so their theorem will tell you how many times a pair appears. Another example. So let's define a function f from CP1 to R. Let's take this to be a Morse function. Let's define xf. I'm probably using the letter x too much. So this will be z in C2 such that, let's see, how do I want to say this? Phi z squared is less than or equal to e to the f of the corresponding point in CP1. So what I'm doing is I'm taking the four-ball, and you can think of this as a very small Morse function. I'm taking the four-ball and I'm perturbing it. So I'm like each hop circle is getting scaled by f, or e to the f of the corresponding point in CP1. And zeta of xf is the product over p, a critical point in f, of so 1 minus t to the e to the f of p to the minus 1 to the Morse index of p. So for each critical point of f, you get a factor, which is 1 minus t to the something, and if it's an even index critical point, then it's going to be 1 over 1 minus t to the something, like in this formula. But if it's a index 1 critical point, then you're going to have 1 minus t to the something in the numerator. So using that formula, it's not hard to just choose your Morse function so that you get a formula which cannot look like this. And so that's how you prove theorem 1. And I should say that the idea of these computations with zeta functions, so I'm kind of running out of time, so I can't say too much, but for the toric domain, you can figure out all the Reeb orbits. So there's a Reeb orbit here of period A, and a Reeb orbit here of period B, and those contribute what you see in the formula. And then there are many more Reeb orbits. So wherever the tangent line to the boundary curve of omega has rational slope, then at that point of omega, so its inverse image in the boundary of x omega is a 2 torus. The 2 torus is foliated by Reeb orbits, whose homology class in the 2 torus is determined by the slope of the tangent line. So it's a one-parameter family of Reeb orbits. In particular, this is a degenerate contact form, because if it's a non-degenerate contact form, the Reeb orbits are isolated. So it's degenerate, but you have this S1 family of Reeb orbits. They all have the same action, and basically they cancel out on the zeta function. So these 2 Reeb orbits you see and everything else cancels. For the XF, this is also degenerate, but there's some sort of easy to see Reeb orbits coming from the critical points of F, and everything else cancels. And in the remaining couple minutes, I should just tell you how do you prove any of this? Where does it come from? So I'll just write some keywords on the board to give you some idea, and you can ask me about it more later. So the basic machinery that we need here is linearized contact homology. So this is a version of Floer homology which is generated by so-called good Reeb orbits on the boundary. It has differential accounts holomorphic cylinders, plus some correction terms. Now there's some technical difficulties with defining this rigorously. It's like John Pardon's work on contact homology is the state of the art on this, but it doesn't quite do linearized contact homology. However, there's a different theory which is positive S1 equivariant symplectic homology. So this theory is completely rigorously defined. And by work of Bourgeois and Lancia, if linearized contact homology is actually well defined, if you're in such an example, which is very rare, but if you're really lucky and all the technical difficulties are okay, then these two theories are isomorphic. So basically, you can use the equivariant symplectic homology to prove theorems, but it's a little more complicated to write down. But you can sort of heuristically think of everything in terms of linearized contact homology. Now, for all the examples I've talked about, this homology is very simple and it doesn't distinguish anything. So if you have a star-shaped domain in R2n, the homology is just a tau root z's in alternating dimensions. So that's not going to classify anything, but there are filtered versions. So this chain complex has a real valued filtration, which the differential decreases. And so from a filter chain complex, you can derive a barcode, as in persistent homology. So that keeps track of so as you increase the action filtration, it keeps track of like what gets canceled out by the differential. The barcode's enough to prove everything I talked about. The zeta function is sort of is obtained from the barcode by throwing out a lot of information. So basically, it just keeps track of the chain complex generators and their actions and gradings. The barcode keeps track of who's connected to whom by the differential. So the zeta function is enough to prove the theorem 1. The barcode proves the theorem 2, which I didn't get to. And that's the, well, hopefully that gives you some idea of what this is about. And there's lots more things to be done in this area. Thank you.
Questions? Comments?
I'm curious if there are applications to billiards in convex domains, like the Birkhoff conjecture, which some people claim to prove, but it's maybe not.
So which conjecture is that?
Birkhoff conjecture, like in a convex domain, you want to know that the periodic orbit somehow is rigid, that the spectrum determines the domain.
I see. Right. Yeah, that could be relevant. So if you take a billiard table, then you take the Lagrangian product, the billiard table with the ball, and then the Reeb dynamics on the boundary of that domain corresponds to the billiard dynamics.
Yeah.
And one can use all this machinery, so one can write down the barcode for that. Yeah, that's a quite interesting thing to play with.
Thank you.
Any more questions?
So what kind of other invariants or information the zeta function carries in code?
What is the zeta function encode?
Yeah.
So I'm not sure. In particular, I'm not sure how, if at all, the zeta function I wrote down relates to more well-known zeta functions that come up in analysis and so on.
Okay.
So it was a bit quick at the end for me. So your theorem said that the zeta function is an invariant of the interior. Are you saying that the barcode is also an invariant?
Yes, the barcode is also an invariant in the interior.
Okay. Yeah.
How would you compare this zeta function with some other invariants in symplectomorphism?
Well, the zeta function is kind of like an Euler characteristic. You say, well, like what's the Euler characteristic? Well, normally it's you take all the chain complex generators and count them with plus or minus 1. Now here we have infinitely many generators. That's not such a good idea, but instead you can count them, instead of counting them with plus or minus 1, you can count them with plus or minus 1 times t to the action. And that's what the kind of information the zeta function is seeing.
Mm-hmm. Okay. Yeah.
You said the notion of barcode is like over-general reactive.
Yes.
If there is another version of zeta function,
I mean, there's some hints of this in a couple other papers which I reference in my papers, but I don't think they've studied this that much.
Okay. Any more questions? Okay. So maybe I also ask a question, right? When you take a filtration, so your filtration is continuous or is it discrete?
Sorry, can you repeat?
When you use filtration to produce barcode, right?
Why do I use
so
the
the
filtration?
filtration is continuous, depends on the parameter, or is a discrete version. Okay.
So the filtration is each chain complex generator has an action, which is a real number.
It's a real number.
So for any real number, you can look at the part of we call it L. You can look at the part of the chain complex where the action is less than L.
I see. So you really produce persistent modules.
Yes, it's really a persistence module.
I see. Actually, the filtration, if you insert some numbers, right? There's also spectral sequence associated. Do you have a look at it? What's the like a higher page or E2 page looks like?
You can certainly do that. I don't know what that tells you.
Okay. Thank you. Yeah. Okay, so if no more questions, let's thank speaker again. Okay.